In this lecture, we're finally going to know what numbers are considered significant in a measurement. So, significant figures in a measurement include all the digits that are known, meaning anything, any line that you can read, plus another digit that is estimated. So, for example, if you have two lines and there is a point in between the two, you could estimate its location. So measurements must always be reported to the correct number of significant figures. This includes labs. So because calculated answers often depend on the number of values used in the calculation are going to depend on the number of significant figures. So if you take a look here, we have a door just like we have in the classroom, and the first meter stick up here only has two marks, the very end, which is 0, and the opposite end, which is 1 meter. So I don't think I can be very certain about how long or how wide this door is, except I know it is greater than 0 and less than 1. So if I were to make a guess, I guess it would be around 0.8 meters. In this answer, there's only one significant figure, because there aren't very many known values. So let's take a look at the next meter stick. So again, we have our lowest value of 0, our highest value of 1, but now it has been divided up into tens. So I can get a little bit better idea of how big this door is. And based on this, I can read that it is larger than 70 centimeters and smaller than 80 centimeters. However, I have to estimate about how far between 70 and 80 centimeters that this door lies. So here my estimation would be about 0.7, meaning it's bigger than the 70 and less than the 80. And 0.77, meaning that I'm estimating that last little area right here. Finally, we get an even more precise measurement here. Again, we have our 0 value on the left, our 1 meter value on the right, our tens units in between that we had before, indicating how many centimeters we have. And now we have the individual centimeters. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 10, so we can be even more precise. So if you were to go from our 0 value, you still see that it is greater than 70 and less than 80, but now you can read that it is it's not exactly on the 7 line. So we know that it is larger than 70 centimeters, but it goes up to the 7th line there and goes a little bit over. So if I had to estimate that meter or that door would be about 0.772 meters or 77.2 centimeters. And we'll get to see this again here in class. So to determine whether a digit or a 0 specifically is significant, that's where things get a little tricky. So you want to make sure that you write down and know the following rules. The first rule is that every non-zero digit to be reported is significant. So anything that is not a 0 is considered significant. 24.7, all of those are significant, so this number has 3 significant figures. 74.3, same thing goes. There are 3 non-zero digits, so you have 3 significant digits. 714, that's also having 3 significant digits, even though there's no decimal point. Zeros are also significant when they appear between 2 non-zero digits. So 7 is a non-zero digit, 3 is a non-zero digit. That means these 2 zeros in between are significant. Same with this one. The 4 is a non-zero digit, the 7 is a non-zero digit, Therefore, that 0 must be significant. Last but not least, it also takes place after the decimal point. So if you have a 5, which is a non-zero digit, and a 3, which is a non-zero digit, that automatically makes this 0 significant. Rule 3 states that the zeros at the end of a number and to the right of the decimal point are always significant. So at the end of our number and to the right of our digit of our decimal point. So 43.00, these are to the right of a decimal point and they are at the end of our number. That shows me that these two zeros are significant. Here we have 1.010. We know that this 0 must be significant because it is sandwiched in between two non-zero numbers. And we know that the final 0 is significant because it's to the right of the decimal point all the way at the end. Last but not least, we also have this guy. All of these digits are significant because we have a 9 point and then everything to the right of that decimal, because this is a real number, is going to be significant. Rule 4 for when zeros are significant is when they are used as coefficients written in scientific notation. So we've already learned how to write in scientific notation. But if you were to write 300 meters in scientific notation, you'd take your decimal point starting on the right, move it to the left 2 times to create the number 3 times 10 to the second meters. Since they are still used as decimal points or as numbers after the decimal point, that shows they are significant and they are used as a coefficient here in scientific notation. Now, there are some exceptions when zeros are not significant. Anytime the 0 appears in front of a non-zero digit, they're not significant. So, for example, 0.0071, all of these zeros are not significant. They are to the left of our significant numbers. They are simply acting as placeholders. Same with 0.42. If I were to get rid of this 0, this is still the same number. It's just a placeholder. Finally, if you have 0.000099, those are all placeholder zeros. And the way that I like to check and see if they act as a placeholder is I like to put them in scientific notation. If I don't have to write them, that shows me that they are simply placeholders. A lot of times they can even show placeholders to show the magnitude of something. So for example, 300 meters, these zeros are considered not significant. Same with all of these 3 zeros in 7,000. And the only non-significant number would be the last 0 in 27,210. There are some exceptions to the rule. Our exceptions are exact numbers. A number that is counted is exact. For example, count how many fingers you have. Do you have 10 fingers or 10 and a half? I hope all of you have 10 fingers, and that is an exact number. There's no guessing, there's no estimated number in that answer. So it is always a measurement having unlimited numbers of significant figures that is counted. The second exception to the rule is whenever you have equalities. So you know that there are 60 minutes in 1 hour. There's not 60.2 minutes in an hour. There's no guessing. It is exactly 60 in 1 exact hour. Therefore, anytime those are defined qualities or quantities, those are considered exact and again have unlimited significant figures. All right, let's give this a shot and determine how many significant figures in each. So in the first one, use your rules to determine how many significant figures. If you came up with 3, that's because 1, 2, and 3 are all non-zero numbers. For B here, you have 1, 2, 3, 4, 5 whole numbers. Now let's see, we have these zeros. We have to determine if they are significant. Because 4 and 5 are non-zero digits, this 0 must be significant. Same goes for the second 0. So overall, you have 5 significant figures. According to our rules, anything at the end of a number, any zeros at the end of a number are significant, and if they are a coefficient in our scientific notation. Therefore, we have 1, 2, 3, 4, 5 significant numbers. 22 meter sticks. Okay, let's think back. Can we count those? Yeah, so since we can specifically count exactly how many meter sticks they have, 22 must be an exact number. Therefore, it has unlimited numbers of significant figures. All right, this one's a little trickier. Remember, zeros before our first significant number are not significant. So these two do not count at the beginning. However, 7 and 8 are considered non-zero numbers. That requires our 0 to be significant between 7 and 8. We also have a 0 at the end of our number. According to our rules, anything to the right of the decimal at the end of our number is considered significant. So overall, we have 1, 2, 3, 4 significant numbers. Finally, we have 98,000. According to our rules, 9 and 8 are non-zero numbers and therefore must be considered significant. However, the last 3 zeros are simply holding are placeholders to hold magnitude. Therefore, these last 3 do not count as significant. And this is also broken down in your notes if you would like to go over all of those. Whenever you are finding all of these significant figures, you also have to have specific rules about addition and subtraction, because the number of significant figures that you keep depends on what kind of calculations you are doing. All of these calculations have to do with rounding, however. So if a digit immediately to the right of your last significant figure is less than 5, you simply drop the rest of those numbers and the value of the last significant digit stays the same. This will make more sense as we practice. If the digit in question is 5 or greater, the value of the digit in the last significant place is increased by 1, and then everything else is dropped off of the number. So let's give this rounding a try. Okay, so we're going to start with the number 314.721. And we want to round this to only 4 significant figures. Right now, we have a total of 1, 2, 3, 4, 5, 6 significant figures. So we have to take the first 4 significant figures, so that would be shown right here as after we numbered them. So we're going to take 314 and since we want to keep this last figure as significant, we have to determine if we should round it. So we look to the right, so we look at the number 2 and determine, does it cause the number 7 to round up or stay the same? Because it is less than 5, that means that the number 7 stays as it is. Here's another example. We have 0.0017